So this is the spirometer, and unfortunately, we're not going to get to look at it tonight, but this is the mouthpiece. And it's really important that you have a good lip seal and the nose is pinched, so no air escapes, right? If you go to the doctor, sometimes they don't even put your nose, the nurse. So it's really important that no air escapes to get a normal reading and a valuable reading. This is just a calibrator, which I'll show you what happens with that. The machine is basically the same as the EKG, just change the data. So this is really important, the patient data, because you're going to get what's called predicted values, like for your demographics. And I'll tell you right now, your actual reading of all the volumes, even the ones we did before, tidal volume and whatnot, your actual is divided by predicted, and that should be greater than or equal to 80%. That's like that standard number in thoracic medicine, at 80% of predicted values. So we have to do gender, you have to type in your age, your height, your weight, and race. So MV, now this one we didn't do yet. This is your minute volume. So now we're getting into liters per minute. So remember, everything we did so far, all those volumes were all done as liters per breath. So now we're taking tidal volume over a minute. Like you see, the graph is still time in seconds of the x-axis, and the y-axis is still volume in liters. So these are tidal volumes, and if you count each one of these over a minute, like inhalation, exhalation, you're going to get the respiratory rate. So I think this is about 20 breaths per minute. So you have to have that to calculate the minute volume. And that's what this stands for, minute volume. So I can't say stroke volume, but this is an average too. Like I would give you this number. Like you're not going to have to take every one of these tidal volumes and divide it by 20. So I would say I'm going to give you this. All these tidal volumes averaged together is 0.6 liters. That's your average TV over a minute. And this is the respiratory rate. So first of all, when you look at this, you have to know that this is minute volume because it's got 60 seconds of tidal volume. It's hard to do, actually. And this, again, is your minute volume. It's a very good one. It's done straight line, good, consistent, quiet breaths, tidal volumes. This is a problem here because probably there wasn't a good lip seal or a nose pinch, right? So that wound up going off the charts. This one's okay. Like you can get this volume even though it was going up a little bit as the air was escaping, but the volumes came out pretty good on this student. So they're both, this is minute volume as well, over a minute, right? Remember, liters per minute now, liters per minute for a minute volume. Liters per minute, really important that you know those units. So far, it was only liters per breath. So, and basically, when you're putting these tests into the spirometer, everything's going to change by the machine. The machine's going to change everything. Like first, you start with the volumes, the lung capacities, which we already did. That was the TV, the IRV, the ERV, the vital capacity, the total lung capacity, and residual volume. Those are all your basic pulmonary capacity volumes. But now you'll actually have to press a button that says SVC, right, on the machine. And it's going to change a few things, like what it looks like for number one. So this value is called your slow vital capacity. So it is vital capacity. And this again, now we're back to liters per breath. Okay. So what happens here is you take a couple of tidal volumes, and then you're asked to take a deep breath in and force the air out. So all you can bring in, all you can bring out. So this 3 values, right? You have TV, you have your IRV, and you have your ERV. So that's your vital capacity. But this is a slow vital capacity. Slow. And another thing that's really important with the last 2 tests, minute volume and slow vital capacity, the first breath that you take on the spirometer is an inhalation. This is inhalation first. Even in minute volume, it's inhalation first. All right. So unfortunately, we're not doing that, especially this pandemic. So minute volume, and actually all the volumes so far were inhalation first. So the coach, like if you were the student's coach, you'd say, okay, you press the button, and as soon as you press the button, you say, take, you know, first you say, put your mouth on the mouthpiece, pinch the nose. Then you say, as soon as I press this button, you're going to take a deep breath in, or you're going to take a tidal volume, inhalation. It's all inhalation. Okay. This is a good one done by a student. Nice tidal volumes, inhalation first, and then a vital capacity. Remember, vital capacity is all 3. Tidal volume plus IRV plus ERV. And it shows a different graph. When the machine does that, when you're asking it to do SVC. This one's okay, but there's no pathology here, just that the student might have held their breath in expiration a little bit too long. So it didn't give you that nice bottom out, kind of flattened at the bottom. So you should be able to recognize, and it's all in your book, that this is SVC. This is not minute volume. It's not the lung capacities. This is SVC. First breath is an inhalation. That's the main thing. This one is your MVV, maximum voluntary, not sure why it's called that, ventilation. This is a tough one. Now, this is only done over 10 seconds in the lab because you'd pass out. So these are all vital capacities. These are all vital capacities over and over in 10 seconds. Could you imagine that? So you're breathing in all the air you can get in, inhalation first, of course, and then breathing out everything over a minute without stopping. You're not going to do that. We would do it for 8 seconds and you'd be dizzy, you know, from either hyperventilating in between or just losing your breath, not being able to recover. So this is more for athletes, or, I mean, we're still going to do this test to check vital capacity over time, you know, but we're not doing this on somebody who's a sick person, right? So this is a really tough thing to do. So you should realize, and make sure you don't call this, you know, VTAC or something like that, because the paper is exactly the same. And we use the same paper for the spirometry as we do for EKG. So this is MV. This is MV right here. Your minute volume, your respiratory rate of 20, and your average tidal volume of 0.6 liters. So this is MV. This is MVV. And this is MVV. So here's the catch now. These are 2 different people. This is like patient 1, this is patient 2. They're 2 different people, so the demographics are going to be completely different. It's like me and Nava. Well, Nava's probably got better MVV than I do. But that doesn't matter, because you're taking the predicted value, what you predict for Finizio, or what you predict for Nava, and then you divide that into the actual to get at least 80%, then you can say it's normal. Right? So you're looking at volume here, right? You can get the volume. I know it's a little off, but you can do the volume of each of these breaths over 10. You'd have to multiply it by 6 to get, right? Because this is liters per minute. This is done over a minute. This is important. But you know MVV is liters per minute. And still inhalation first. So your outcome is going to be different. Like this happens to be somebody who's possibly a triathlete who happens to play the saxophone or something, a musician that uses his wind, right? So the volumes are huge, you know, but the demographic is different as well. So you have to kind of take that into account. This is actually a student. So predicted values divided into the actual will give you hopefully 80% or better. So I have to give you the predicted values. All right, makes sense? Any questions so far? Again, know the units. Know what the test looks like what the difference between the capacities and the volumes versus the SVC, MV, and which other one do we see? MVV. And they're all in your book. Pretty straightforward, actually. Okay, now things change. Now you're going to enter, now I want to do FVC, which is forced vital capacity. Now remember, this is vital capacity. That involves tidal volume plus a full inspiration, IRV, and a full expiration, ERV. So we're taking into account an inhalation and an exhalation. But listen to this. FVC, the first breath is exhalation into the spirometer.
So this has two different graphs.
So now you're going to tell the student, okay, when I press the button, well, first you're going to tell them, you're going to take a deep breath in, as much as you can take in. And when I press the button, you put your mouth on the mouthpiece and you blow that air out as hard and full and fast as you can. So we're testing exhalation. Everybody agree here? Yeah. FVC is testing exhalation. So now we're looking for more obstructive conditions. Yeah? Those bugs have been everywhere. I think it's a beetle. I think it's a beetle or a cricket that they're using in a lab. It might be a grasshopper, so you might not, technically you're not supposed to kill those. I think it's inhibited by law. So anyway, that bug's the only one in here, so I saw him before. So now, I know I saw that last thing. So now, this is your FVC, your forced vital capacity. All right. So this was kind of done wrong, and I'll tell you why. Because this breath should have started at 0, but the problem was like either the student pressed the button too quick and didn't match up with the exhalation. So we can still use this. You see what I'm saying? Like this line here should have started there, but I could still get a reading. I could still get the volume. You see, because this is still volume in liters over here, and this is your time in seconds. The time is not that important yet, but I'll show you. So what do you think that volume is of FVC there? It's like a little before 6. So 5.8 maybe, something like that. That makes sense to everyone? Yeah. That's the volume. So it depends on the person. Like if the predicted value is 6, then you multiply 6, divide 6 into the 5.8. And hopefully that will give you above 80%. And that would be within normal limits for that person, that demographic. Okay. So FVC, now the machine changes it to look like this. So this is all exhalation coming up here. This is exhalation. Okay. Don't worry about this chart yet. This completely changes everything. And Dr. Lee will go over this in lecture, but I just want to introduce this particular graph in a minute. Okay, so can we agree now that this is exhalation, full volume that comes out? And we're going to be able to really decide if this is a COPD. Question?
How do you just, without seeing anything else, you know that it's FVC?
Yeah, because that's what you put into the machine. And this, nothing looks like this. This is the only one that looks
So
like
you,
this.
are you just gonna give me as like plain pictures?
Yeah, it's in your book. It's in your book and in the PowerPoint. So know what they look like. That's an easy way. That's an easy way that this is FVC. It's not SVC.
And asking for one breath.
What's that?
Asking for one breath.
Yes, one breath.
Okay, cool. So that's different.
Liters per breath. You got it. Very good. Not over a minute. Correct. One breath is all you need for this. So this is a better depiction. Now, this is a good one. This one, the student, this is FVC. And this is FVC, the one we saw before. The one on the right is not FVC. These two, patient 1 and patient 2, they're two different people. These belong to the same person. But these two are different people. Like this is patient 1, this is patient 2. Two different people, got it? And demographics are completely different. So the predicted values are going to be different. So FVC, this is a good one. Like I said, you started right on the 0. They blew into the exhalation into the spirometer right when the button was pushed. And you got a volume of like, say, 3.4. Does that look right? We could agree? I'll give you the numbers, but I mean, you might be able, this is very easy to see, but you have to remember this is volume in liters, and this is time in seconds on the x-axis. Y-axis is volume. So 3.4, everybody agree? The bug, does the bug agree? I almost killed them before I didn't. So you see that? You guys at home okay with this so far? Please ask. If you're not, we're all together on this. Okay, so this is the other guy or girl, and it's okay. They started late, but it's okay. I still got the volume, which was 5.8, we'll say. So here's what we got to do here, and this is really important. We take the first second, and you can do that here too. You just have to put it there. You kind of have to extrapolate that up in a straight line. So what we're going to do is take the first second of FVC, the first second, and that's called your forced exhalation volume in the first second, your FEV1. Okay, so that's what it's in the first second. So let's say what did we say the FVC was there, 3.4? Yeah, the top one, patient 1. So if the FEV1 is 3, you can get a ratio now. So the FEV1, forced exhalation in 1 second of FVC, divided by your FVC. So you'll divide the 3 by your 3.4, and that should be above 80%. 80% is the golden number so far.
Okay.
So that's called the FEV1 FVC ratio. And this is really all exhalation, testing for COPD, for obstructive conditions like emphysema, chronic bronchitis, or asthma, right? So now this one on this side, this is a flow volume loop. Now this one is going to come out, or a diagram, or whatever Dr. Lee is going to call this, but it's flow and volume. So the machine will take the FVC and convert it to this chart. So again, all you have to do is know that what this is. It's a flow volume loop that's based on the FVC. So now the y-axis changes, and that's really important. So this is velocity now in liters per second. So how fast did you get that air out? And this is like 6, little below 7 liters per second. So we can tell what that is. And what does this look? And this is all exhalation. The top is all exhalation, which is really confusing. That's what the machine does. The bottom is inhalation. What does that look like to you? Kevin, what does that look like to you? An upside down what? What does it look like?
Like the weight?
Like an ice cream cone.
Oh, I don't know, the weight or something.
Could be. It looks like an upside down ice cream cone, right? Where the top is the pointy bottom of the cone. And this is the ice cream. So this is normal. This is normal. And the bottom one's normal too, but I'll tell you what happened there. So now if you have COPD, this top is not going to be pointy. It's going to flatten out, which Dr. Lee will show you in lecture. But this is not FBC now. Everything changed because the machine changed it. Question?
Can you get like the total capacity from like the top one?
No, you can't get any of that from this.
Oh,
You
okay.
can't get any of that. It's a good question. You can get FVC though, because this is the velocity on the y-axis. The x-axis is still volume. So see how it matches up that 3.4
Yeah.
over this way, which is really confusing. But you're not going to have to do that. I just want you to know that this is not a typical FVC. This is a flow volume loop. And the one on the bottom, different patient, it's all good. This is all good. This is normal exhalation, normal. It's like 13 liters per second. But the bottom, what happened here, and this is inhalation, they probably stopped their inhalation. They didn't let it flow out. So it kind of cut it off. So that's not a pathology. Although it looks like somebody took a bite out of the ice cream cone. So no, this is a perfect FVC. But these are two different patients, right? So, and again, we can get the FEV1 by just bringing a line up here. We just can't, start at 1 second. We got to start over here as the first second of FBC, which is called FEV1. Really important for exhalation. This is all exhalation. Now, AVR is very important. Remember minute volume, which is liters per minute. And this is a minute volume test, right? This is minute volume. Anybody have a calculator ready, please? So your minute volume, and I'll give you the numbers basically, except for the respiratory rate you should be able to get by counting the hills. So the minute volume equals the tidal volume, which I told you was 0.6 liters. And then you multiply the respiratory rate, which is 20. And what is the minute volume for this person? 0.6 times 20. Anybody have a calculator? What'd you get? 12, yeah. 12 liters per minute. Very good. So now we want to calculate a much more important value called the alveolar ventilation rate. Now this is important because this is the actual air that's going to be used for gas exchange. So it kind of takes off a little bit of the MV. So this number right here, 0.15 liters, is what's called anatomical dead space.
So is that kind of like residual?
It's not. That's a good question. It's different than residual volume. This is just the anatomical, like Dr. Lee may talk about physiological dead space and it varies from person to person. But this is a very generic number that they use across the board in thoracic medicine to calculate AVR. So this is what we're going to use in lab. So to get the AVR, you take the TV, which is 0.6, and right off the bat, you have to subtract 0.15. And what do you get with that? Times your respiratory rate, which is 20, which equals what?
9.
So that's 9 liters per minute that are actually, that volume is actually getting to be used for gas exchange in the alveolus. Okay. It's a very generic number. Like Dr. Lee's going to go into that more. But for lab, that's the only thing you really have to calculate. I'll probably give you these two numbers, and then you give me the MV, and then you give me the AVR. So you have to memorize that value for anatomical dead space, right? Maybe the respiratory bronchioles, where the air is not used, right? Or that volume that's present is not used for gas exchange. So the air is getting there, but not everything. So it's like 75% of what comes in is used for gas exchange. Make sense? Yeah, that's, and of course the question will be like in your book when you're doing your questions, that is more important. AVR is more important than MV because that's what we use to oxygenate our blood, right? Very important. So go through these questions. We'll do it in the SEC, and I'll probably have like a formal review for this class. Like on Sunday or Saturday, I'll have like a happy hour. We'll get together and we'll go through all and make sure you got all the right answers, right,
Okay.
in your book. So if you don't get them in the SEC, we'll get it done on the weekend, okay? So I'll send out, and we'll do it through the SEC, but, so Isabel, don't worry, I'll get you in, I promise. We'll do it over the weekend, like Saturday would be perfect for me, like 3 or 4 o'clock. So keep that in mind, right? And if I don't do it through the SEC, I'll just do it through Zoom, okay? So make sure you show up to that, because that'll be really helpful. Okay, so here we're gonna do some problems. Doing good so far. And here's the values you've already heard of, your FEV1, FVC, and this is the FEV1 FVC ratio. Okay, and of course these numbers have to be given to you. You're not gonna have to figure these out unless I show you a really good FVC that has really good lines on it and you can tell the volumes clearly. Okay, so now we're talking about obstructive versus restrictive conditions. So you know the obstructive, you know 1 or 2 restrictive. So within normal limits, somebody who doesn't have either obstructive or restrictive, the FEV1 is going to be normal. Okay, 80% of predicted. 80% of predicted is normal. 80% of predicted value. FVC is going to be normal, and the FEV1 FVC ratio will be normal. In obstructive, of course, the FEV1 is going to be low because they can't get the air out. Obstructive is an exhalation problem. So that first second is going to be a low volume. FVC is always low in both because that's vital capacity. That involves both inspiratory and expiratory function, inhalation and exhalation. So that's always going to be low in both conditions because they involve both. And in obstructive, of course, you can have, if your FEV1 is low and your FVC is low, your ratio is going to be low, FEV1 to FVC. Now here's the catch. In restrictive, your expiration is okay. So your FEV1 is going to be normal. But always, because it's vital capacity, which vital capacity equals TV plus IRV plus ERV, and this is inspiratory, right? This is inspiratory or inhalation. This is a problem, and that's a problem with inspiration. This is a problem with exhalation, expiration or exhalation. That's where the problem lies. Okay, so an FEV1 FVC for restrictive is going to be normal, greater than or equal to 80%. So you can memorize this, kind of like you did what you did with axis evaluation, but you should understand why as we go before we get to the lecture part. So get your calculators ready, please. You can't really eyeball these. You really have to do the math. So here's what you're given. I got to give you the predicted for both FEV1 and for FVC. So here's your actual, what you blew, what you exhaled in the first second of FVC was 2.2 liters. So you divide 2.2 by 5, and what do you get? Yeah?
0.4.
So 44%. Yeah, like he said, you just got to multiply by 100. So it's 44%. That is way below 80%. So that is low. So let's do the FVC. Divide 3.4 by its predicted value for this person, case 1. Divide by 6. 3.4 divided by 6, what do we get there?
56.6%.
And that's way below 80%, so that is low. Then we could do the FEV1 FVC ratio, 2.2 divided by 3.4. What do we get there?
64, like 65%.
Lower than 80%, so that's low. So what do we have here? What can we write? Within normal limits, this case, is it obstructive or is it restrictive? They're all low. That's obstructive. Yeah, so write a big O in your book. But I think it's the same problem. I think the same numbers. That's obstructive. Case 2, given, all this is given to you. Predicted values for FEV1 and FVC. So the first exhalation and first second of FVC was 3.4 liters. So this looks pretty good. So if you divide 3.4 by 3.5, what do you get? It's probably in the 97%. So that we call within normal limits. Let's check the FVC, vital capacity, forced vital capacity. First breath was an exhalation.
95%.
So 3.8 divided by 4 was 95%. So that looks pretty good too. Within normal limits. Then we can get the FEV1 FVC ratio, 3.4 divided by 3.8. What do we get there?
89%.
Yeah, that's good. That's fine. So this does not have an obstructive or restrictive condition.
Wait, when do you say when it's high?
Sometimes that happens, but we're not going to do that. Sometimes you happen. So usually when it's high, I think like next thing we do when we do pathologies, it's usually if it's above 120%.
Okay. So
Yeah, that's considered high. You know, like if you think about emphysema, right, where you can't get the air out. So what value in the lung capacities would be high if you can't get air out? The residual volume, right? The residual volume would increase because you have the air trapped. So that would increase your TLC possibly by a lot. And that would, if that goes above 120%, that would be abnormal. That wouldn't be. So that's the only time that would happen. So here it's not going to happen. Like it's not going to happen here. Because we're just looking for normal obstructive versus restrictive. Good question. So here's case 3. You have your predicted and then your actual FEV1. And what do you get for that one?
83%.
83%, right? So it just barely makes within normal limits. Something's not right there. We'll see. So here in FVC, predicted for this case 3 is 5, and the actual FVC was 3.1. What do we get there?
62%.
62 is low, below 80%. So right now we're thinking, well, it can't be obstructive because this is normal. So it's possibly restrictive. Let's double check. And 2.9 divided by 3.1. What percent did you get there?
94%.
So 94 is within normal limits. And this means that this one is what? Not obstructive, but restrictive. Because you have this. And that's vital capacity, forced vital capacity. Even though it started with an exhalation, it's still vital capacity. Really keen on obstructive conditions, though. So this is just filling those in. Let me just go through this list with you. This is in your book. I don't know, what page is that, Mary? 130, page 130, and we'll probably end it there. So these are conditions that could be caused by obstructive or cause obstructive problems. So right away, you know the obstruction of an airway, of course, like especially during exhalation. Emphysema, obstructive. Chronic bronchitis, obstructive. Asthma, obstructive. So that's your COPD, right? Those 3 conditions. Cystic fibrosis is obstructive, like the mucus we talked about before. So everything else is restrictive, like changes in the pleura, bringing air in. Pulmonary fibrosis, like that could be asbestos or something that causes interstitial fibrosis in the airways. Bronchiectasis is very acute constriction of the bronchi, which restricts the air coming in. Change in your spinal curve, which can compromise your respiratory system, is more restrictive. Sarcoidosis, which is granulomas, like connective tissue disease, makes it hard to get air in, so that's restrictive. Other non-muscular diseases of the chest wall is restrictive. And this pneumonitis is more about your pneumonia, right? Pneumonia is more restrictive all the time. Okay, so that's where we'll end. Anybody have any questions? Anybody at home have anything?
Okay, so we'll go to
I just need clarification on something.